to have that there. Remember that. And we get to this example, and this is where I hope, for those of you that have had physics before, like the magic will happen, and you'll be like, whoa. Those of you that have not had physics before, I think you'll still get it. We can approach it from two different perspectives, like calculus or physics, or kind of both. And we'll just kind of see where we end up. So it says, a baseball is thrown upward from a height of 2 meters with an initial velocity, and we probably should say initial vertical velocity of 10 meters per second. Determine the maximum height. And you got to be honest, like if you were a physics student, you'd probably busily be getting to work with some kinematics, right? The things you maybe memorized, having your notes sheet or whatever. If you're a calculus student, you're going to look at this and maybe you're going to say, I really, Mr. Anderson, think that you did not give us nearly enough information, because maybe you noticed this. I said, determine the maximum height, and I really didn't tell you a whole lot about height other than apparently this baseball started at 2 meters height. Somebody threw it up in the air. That's kind of it, right? Like I told you how the story started. And I'm asking you, kind of how the story ends, but I didn't really give you much of anything in between. So physics people can maybe help us with this a little bit. Once this baseball is launched, once the person has thrown it in physics, we classically ignore wind resistance or air resistance. So neglecting wind resistance, once this person releases a ball, there's only one force acting on the ball, and that would be? Gravity. What kind of a thing is gravity?
It's a constant.
It's a constant force, and what does a force produce on something with mass? Acceleration, right? So, what is the acceleration due to gravity using meters and seconds? Physics people, please? Oh my gosh. You better pray that your physics teachers don't watch this video.
Is it acceleration?
It's acceleration. So what is the acceleration due to gravity measured in meter? Negative. Hey, there we go. We usually make it negative because it is causing the height to decrease. And so I'm going to say A, which is acceleration, equals negative 9.8, and that would be measured in meters per second squared. I'm not going to get too hung up on the units right now. Okay, so maybe the non-physics people didn't know that, and that's okay. And you don't have to have that memorized for this class, really. But there it is. So here's where we're going to do a bit of calculus with this. Acceleration is a rate of change, is it not? So whether you're in physics or not, you should be able to think this through. Acceleration is definitely a rate of change. It's the rate of change of what? It's the rate of change of velocity. So what I'm going to do is I'm going to respell acceleration. And here's how I'm going to respell it. Why on earth would that be important to do? Yeah, so let's go back up to that the fill in the blanks at the top. Notice it says the antiderivative of acceleration will give you a velocity function. The antiderivative of a velocity function will give you a position function. Why on earth would I be interested in going back to finding a velocity function and then maybe a position function? Why would I want to do that? Why would I be interested in finding a velocity? Like right now, the only thing I have is an acceleration function. That's it. I have no other relationships. Why on earth would I be interested? Why would I care about finding a velocity function or maybe a position function? Why is this position within this unit where it is? What do you think, Robbie?
Find max and mins
of?
A.
Find max and mins of what?
Of acceleration.
I don't really want to find a max of acceleration. What do I want to find? I do want to find a max.
I know that's what it is, but it eventually gives you the max of y.
What? So you're using a lot of really vague words. You said it eventually gives you the max of y.
Yeah.
But you said it, and I'm not trying to be a pain, Robbie.
The derivative of antiderivative.
Gives you the maximum height when velocity is 0.
Okay, now we're talking physics-y kind of stuff. So let's go back. What is our objective? What is this question asking us to do?
Find the maximum height.
Would you not think then that having a function for height might be useful? If I want to know what the max height is, and I don't have a height function, might I seek one out? Does that make sense? Now we'll get to this maximum height thing. We'll figure out, like, is this when v is 0 and all that stuff. We'll try to connect all those things. But listen, have you ever had a math problem and you just thought to yourself, if someone would just tell me how to start, I'd be good? That's what I'm trying to do right now. The question of why would I do this, isn't that kind of a starting question? Are you with me? Why would I do this? Who cares? Oh, I'm trying to find a max height, so it might be beneficial to have a function describing height, which I don't have yet, right? Sam?
Well, you could probably use, well, right now, what we have is a constant. Acceleration is
Yep.
constant throughout, so it's hard to tell anything about the character of what's going on.
Going on with what?
Going on with the ball, and
I know its acceleration is negative.
but it's hard to tell where anything is different from any
Mhm.
other time. Cause
And so in order to be able to tell those things, what would we need?
we should find a velocity time function, I think. Well, at least that's the first step, so at least
Yeah.
we can tell when the velocity is 0.
And based on what you saw above, if I had a velocity function, what else could I find?
Position.
A height function, a position function. Yeah, that makes sense. And I think we need to hit all these steps along the way. What I want to get is, do you understand why? Like, you said yes or no? No? Okay. Again, let's go back. Let's go back to a little bit of chapter 3 kind of stuff. Remember, I wrote it all the way across the board. I said something along the lines, to find a max or min of blank. In other words, you could fill in the blank with whatever you want. You need to set blank prime equal to 0 / DNE. Do you remember that? So if I'm trying to maximize height, I need to set h prime equal to 0. So doesn't it make sense that I would need a height function? And what's the only way you can go from an acceleration, which is what I have, and end up eventually with a height function? Darn autoplay. Probably should just get off that website. You with me? Come on. And then another one, right? So does that make sense? I want to get to a height function. Do you understand why I want to get to a height function? It's asking me about maximum
Because it wants the height.
height. And so if you don't have a height function, it is going to be darn difficult to figure out what the max height is. That make sense?
Yeah.
Okay. That's why we're doing what we're doing. Because honestly, if you don't know why we're doing what we're doing, you won't know when to do what we're doing. Make sense? I could hand you a hammer and nails and a board and just say, and let you figure out what to do, and you could just sit there and just start hammering nails into the board. And until you ask why, you won't even know what you're doing. If I was like, hey, I need you to put this together because we're going to build something for this Algebra 1 class, and here are the plans, now you get it, right? I'm trying to help you understand why. You with me? Okay. So if I'm going to try to find a velocity function, we need to do an antiderivative. To do an antiderivative, I need to separate my variables first, right? Okay, so I'm going to multiply the dt over. That'll give me dv is equal to negative 9.8 dt.
Why do you have that equal to 9, or acceleration?
Because acceleration due to gravity in metric is negative 9.8 meters per second squared. That's either something that I have to tell you, or you'd have to memorize, or you just have to look it up on Google. It would take you however long you can type.
But I mean, like, why did you set equal to 9?
Because acceleration due to gravity is negative 9.8 meters per second squared.
And you're just going to go backwards from this.
Yeah, I'm going to go backwards. That's right. Okay,
Wait, can you explain again how you got to the dv equals -9.8 dt?
so what I did is I multiplied both sides by dt.
Oh.
Right, so this, hey guys, maybe I should connect this a little bit better for you. Do you guys remember yesterday I made this big old deal and I slowed way down and I said, if you're solving a differential equation to earn any points at all, you need to
Show what dv is.
show the separation of variables. So do you see how I just did that? So you've got to show that. If you're solving a differential equation, got to show that. Okay, so then if I am trying to get to a velocity function, and what I have is the differential of a velocity function, how do I undo a differential? Yay, I do the antiderivative. So I'll do that to both sides. What's the antiderivative of dv? It's v. And what about the other side? Negative 9.8 dt, the antiderivative? Negative 9.8, and it shouldn't be an x because our independent variable is a t, so it'd be t, and then don't forget the plus c. Okay, the plus c is a little bit of a problem because we have no idea what it is yet, but we can figure it out. Robbie?
We don't have c?
Sorry?
We don't have C? I thought it gave it.
Well, I said not yet. We'll get there. Do we have any information about the velocity at any point, any time? What do we know? The initial velocity. What does initial mean? Starting. So when t is
0.
so in other words, when t is 0, v is 10. We could use that, can't we? When t is 0, that means t is 0, v is 10. Look at that. So negative 9.8 times 0 is 0, and 10 just equals c. So now I have a much better picture of what my velocity function is. It is negative 9.8t plus 10. Still hanging in there with me? Now, if you've had physics, you probably recognize this as the VF, or the final velocity equation, maybe? VF equals V initial plus AT. Anyway, maybe not that many of you have had physics. Some of you are looking at me like, what are you talking about? Whatever. Okay. Remember, if I'm trying to find a max height, what should I have to have? Oh, no. I don't think so. If I'm trying to find a height, I need a height function, right? I need a height function. I already have a velocity one. It's okay. So wait a minute. How on earth, I figured out how to go from acceleration function to some kind of velocity function right there. How am I supposed to get to a height or a position function?
The antiderivative of velocity.
Yay. So let's do this. I'm going to respell velocity. I'm going to respell velocity like this. I hope you're paying close attention. Would you guys agree with me that the rate of change of height, represented by dh dt, that is velocity, right? Like dh dt is the exact same thing as velocity. Negative 9.8 t plus 10. H stands for height because the guy threw the ball straight up in the air, so we're saying vertical velocity.
Could be Y.
Could be y, sure. I like h for height, but whatever. Okay, if I'm going to be trying to go back to finding a height function, and I'm going to be doing some antiderivatives like you guys suggested, what do I have to do first? Separate variables. Yes, so I would get, if I did that, dh equals negative 9.8t plus 10 times dt. Let's multiply the dt on over to the other side. Okay, and then finally, remember I've been making this big deal about this whole time. Like, if you want to find a height, you need a height function, right? Aren't we almost there?
Yeah.
What's the last thing I need to do to get there? There you go. That's right. So antiderivative of both sides. The result of that would be, well, the left side would give me what? H equals, now if it's negative 9.8t, isn't it that power rule? Do we need to add 1 to the exponent? So it'd be t squared, and it'd be negative 9.8 divided by 2, which is negative 4.9. Yeah, just using the power rule for antiderivatives. What's the antiderivative of 10? 10t. Let's be careful not to mix up our variables. I know we're in this habit of everything's an x, and I'll give you a lot of things are x's. I give you that, but these are t's. And then don't forget the plus c when you do your antiderivative. So in order to finish this up, I need to have some information about height to help me find my c. Do we know anything about height at any time in this? 2, yeah, height of 2 meters when what? T is 0, height is 2. We're getting that from right here. The ball is thrown upward from a height of 2 meters. That means at the start, t equals 0, height is 2. So I'll say 2 equals negative 4.9 times 0 squared plus 10 times 0 plus c. Well, anything times 0, any real number times 0 is 0. So I find out pretty quickly that 2 is equal to c. So my final height function is right here. And this is where I hope we'll be able to make some beautiful connections with physics. So here is what a physics person would probably say. I'm trying to find a maximum height. Threw something in the air, right? The maximum height will happen. Please don't text in the middle of my class. Please, Adelina. Well, if you're having an emergency, you go take care of it. But please don't, yeah. It's like the third time in the last couple of weeks I said, please don't text in my room. I'm starting to feel slightly disrespectful. Okay, but it's not about me. It's about this. A physics person is going to say, wow, the max height will happen whenever the velocity is what? 0. And that makes sense, right? Like what goes up must come down. So if the velocity is positive, 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 and then negative, 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 then somewhere up there the velocity had to be 0. And that would have had to be the max height, right? For like that one instant, there's no vertical velocity. So a physics student's going to be like, oh, I know how to do this. I'm going to say, I'll just show you a little comparison here. Physics student will say, this is when, this max height is going to be when v equals 0. And they'd say, well, I got this lovely velocity function, so I'm going to say 0 equals negative 9.8t plus 10. And they'll solve that. Can anybody divide 10 by 9.8 real quick for me, please, on your calculator? Obviously, it's 1 point something. 10 divided by 9.8. 1.02, any more decimals? 0? Okay, cool. All right, awesome. So they're going to say, well, that's the time when I hit my max height. But then a calculus student would maybe approach this a little bit differently. They're not going to say necessarily directly, hey, the max height will happen when velocity is 0. They're going to say, oh, I'm trying to maximize height, and that would happen when? H prime equals 0 / dne. Well, so they'd come over here and they'd say, looking for when H prime is 0, because I'm trying to maximize height. And then maybe they'd think for a second, well, wait a minute, what's the rate of change of height? That's actually velocity, right? So it looks like they're disagreeing, but they're actually agreeing, aren't they? So H prime equals 0. So they'd say, all right, well, the derivative of height, well, that's negative 9.8t plus 10. And if they hadn't figured it out by this point, they'd eventually be like, oh, H prime must be v, right? It's the same thing. And then they'd get the exact same time answer, of course. The physics student never feels compelled to justify themselves. Unless you're in Physics 1, you probably have to write like a paragraph about it, right? Physics 1 students? Yes? Not easy. A calculus student maybe would justify themselves. Can anybody tell me what would be the easiest, super quick way to justify yourself to say that you actually do have a maximum when t equals 1.020? Second derivative test. Why on earth would the second derivative test be so easy? We already have it. What's the second derivative of height? Negative 9.8. Isn't it the acceleration function? Yeah. So I could then say a of, actually I'll just say it like this. I'll say h double prime of 1.020 equals negative 9.8, which of course is negative. Therefore, h is maximized when t equals 1.020. Does that make sense? You could do a first derivative test and say, hey, velocity changed from positive to negative at 1.020. You don't have to. Final thing you'd have to do is actually find the height. So whether you're in physics or calculus, the final step would be to say, oh, okay, well, we found out that that's when the max height happens. This actually asks for what is the max height. So regardless of who you are, if you're going to be doing that, we're going to just find h of 1.020. And you obviously just use your height function right there. You just do a little arithmetic on the calculator. You're going to come up with a height for that particular time. What do you think? Questions? Physics people, isn't that cool? Like there's your kinematic right there. Your kinematic in the green box. Kinematic for position. We didn't start out with anything. I didn't say, guys, hey, you need to memorize this stuff. All I said is, what's gravity? And we worked our way backwards to get to this kinematic that you had to memorize for other classes. That's where it came from. It didn't come from, Newton sat down for a couple weeks and just came up with it. Just made it up. It's developed, right? Has a reason for what it is. Anybody come up with that height? 70-something?
Yeah, 7.102.
7.102 meters. Okay. Fair enough. Guys, questions, concerns, comments about anything? Yes, ma'am.
Would you have to justify your height answer, or is the justification for your calculus?
I think the justification, so like over here, like what we've done is we have justified that when t equals 1.020, height is maximized.
Yeah.
And so we've done all the justifying we need. And so then the height itself is just the output for the time that we know to be the maximum occurring. Yeah. Yeah, so you don't have to go back and like re-justify the 7.102 because we already justified the time that goes with that. Yep. Other questions, concerns, comments? Yeah, Robbie.
Would we need to show all on the?
So I left the question the way that it's worded somewhat vague. If I want you to do what I want you to do, I'm going to say, hey, show me how you solve the differential equations, show your separation of variables, show all your steps, that kind of thing. So I'll make it pretty darn clear. But the general rule would be is if you are solving a differential equation, you better show separation of variables, you better show your antiderivatives. And I guess furthermore, based on instructions, hopefully this will be a relief to all you guys. Based on instructions and even just like the content of the question, it will never be like a life or death advantage for a physics student versus a non-physics student. Make sense? I mean, a physics student might be able to say, well, you know, hey, I was a little more well-versed in meters per second and velocities and things like that, so I might have had a little advantage just because I've had this other class. But there will not be a question in which your physics knowledge or memorization of kinematics is going to make the difference, right, between like knowing what to do or being kind of clueless. Make sense? So in other words, you can't just be like, I know the kinematic for that, plug, done.
So would we have to like go all the way back?
Again, if I want you to do that, I'm going to write that into the question in such a way that if you actually read the instructions, it's unavoidable. Yeah. Anybody else? Okay, cool. So I hope you guys enjoyed reading, or I should say watching and learning a little bit about area. You guys good with the idea that like all of the area formulas within this were like ultra easy? What was the area formula used repeatedly? Sorry? Yeah, but how do you find the area of a rectangle? Base times height. And I got to tell you guys today, and really a large part of next week, and so I guess somebody could easily say, you know, a large part of the semester is next semester as well is going to be simply about base times height. Honestly, and all of its various looks and forms and shapes it can take. It's going to be about, can you find the area of a rectangle? And do you really know what that means? That'll be kind of the question. So we talked about left sums, we talked about right sums, midpoint sums, that kind of stuff. Within there was a couple of examples. 2 and 3 are pretty darn rigorous. Like you got to like really like build your own little table and think about your graph. I thought this was a good one to kind of start off with. This question right here, a little bit more like what you would be expected to perform on a quiz or a test, something like that. If you're not already comfortable with tabular data, I hope that you do get more comfortable. We do tabular data a lot. We've already done it, and we'll keep doing it. So here goes. Let's read this. It says, a polynomial function f of x is differentiable and continuous on 0, 8. Selected values of f are given below. And then 2 things we're supposed to do. Use a left sum to approximate the area under the curve. Use a right sum to approximate the area under the curve. So what I'm going to do here first to help you with this, I want to show you a way, and then I'll kind of show you what I would encourage you to shoot for, to try to get to. You look at a table like this, and I got to admit, I can see why someone would look at this and be like, oh my gosh, a table, this is so hard to visualize. And if anything is ever difficult to visualize, what should you do? Draw a picture, draw a graph. I agree. So that's what I'm going to do. I am going to just take a second and make a y-axis and an x-axis. And please forgive me, I'm sure my scale is going to be off at some point. And I'm just going to plot some points. I mean, I can see obviously the high point is 242. And let's see here. So I'm going to say that 0, 18 is like right there. 132 would then be like right about there, let's say. 372. It's going to be up there a bit higher. Gets a little bit steeper in there. And then it gets really steep, right? So 7,200. There's 7, and we're going to say that 200, we'll put it like way up there. Come on. And then 8,242 would be just a little higher than that. Like so. Okay, so we got this graph, and here's the honest truth. We have absolutely no idea what this graph is doing in between. I mean, it literally could be almost linear, or it could be that. I mean, it could be all kinds of stuff. We know nothing about this graph other than those data points, right? Okay, so what we're supposed to do is estimate the area under the curve using first a left sum. So if you remember from the video, a left sum is named left sum because the height is found on the left side of the interval, right? So you just see I've got several intervals here. I'll use color again. So there's an orange interval, and there is a red interval, and a blue one, and a purple one. So let me just ask you this. If I'm going to be doing a left sum, and I'm going to use that first interval to create a rectangle, anybody have any idea what the height would be that I'd use for a left sum on the first rectangle?
0.
No? 18. Yeah, my heights are my y's. And so what I'm going to do is I would construct a little rectangle, and it would look something like that. Do you see how I've used the left side of the interval? So my first rectangle would be this area. I would say area is approximately, or area under the curve is approximately. My first base length is 1, and my height is based on the left side, and it's 18. 1 by 18. So I'm using this data right here. Well, the next one, the red one, a little bit different. I'm going to draw that one in based on the left height. My left sum is going to come in about like this on that red interval. So on the red interval, what height do you think we'd use?
32.
Say again? 32. So using this set of data. So my next area, what would be the base length for this? It would be 2, right? The difference between 1 and 3 is 2. And it would be times the left height, which is 32. You guys got the hang of this? Let's just see if you can finish it out. I'll just quietly work up here. You feel free to peek if you want. I'll just work quietly. We'll see what we end up with. I think I messed up my arithmetic. You guys get the same thing I did?
570.
570? Yeah. Okay. So I tried to color code stuff. Is this making sense? Orange goes with orange, red with red, blue with blue, purple with purple. What is the one height that did not get used? Doesn't that make sense? Well, no, height is actually an x value, right? So the 242, right? Yeah, 242 didn't get used. Why would the 242 not get used?
There's no box, but like there's no more area.
Yeah, we're doing a left sum, right? And that's where it ends. So there's nothing to the right of that, and so it won't be used in a left sum. That'll be the case for a left sum. You'll never use the final data point. Okay? I got 570. Can I mention a couple things to you guys about what would I expect to see on a quiz or test? So if I ask you to do a left sum, I need to see evidence that you actually did a left sum, like using rectangles. And so if you're like really good and you do stuff in your head, or maybe you did stuff in the calculator because the calculator is active, but the only thing you wrote was the thing in the purple box, be prepared to get nothing. Not half credit, get nothing credit, right? I want to see evidence that you did a left sum. What is the best evidence of the left sum on my page up there? No, I don't think the graph is... Yeah, my colored equation, right? This right here, this is a great evidence that I used a left sum. Because I got to be honest with you, what I think you should work towards is I think you should work towards doing this with no graph. Can I give you an example of that? So here's what I would want you to work towards doing, and I'll show you with the right sum. I'm going to say for this right sum, I'm going to use the exact same data in my table, but I'm not going to draw a graph. Here's what I'm going to do. I'm going to say area is approximately equal to, my first rectangle is between these two, right? I'm going to say my base length is 1, and my height is not 18 because I'm using the right side, and my height would be 32. That make sense? I'm not using the graph at all. My next rectangle is going to be here. And I'm going to say the difference between 1 and 3 is 2, so my base is 2. But I'm going to use the 72, right? I'm using the right side of every interval, not the left side, because I'm doing a right sum this time. So times 72. And then the next rectangle would be here. Base length again, just like before, is 4. I'm not going to use the left side, I'm going to use the right side. So it'd be 200. And then my last interval, my last rectangle would be from 7 to 8. Base length is 1. I'll use the right side for my height, 242. That's what I would want you to do. Does that make sense? So if you want to do a graph, do it. It's great. And I think if you're struggling at all, that's exactly what you should do. But I'd love for you to get to the point where you can just pull the data right out of the table, show me, similar to this, how you did a right sum in this case, and then we get the answer once we do a little arithmetic. Because often the calculator is going to be active on these because, I don't know, those numbers are kind of large, and it's expecting a lot to have you just be perfect with large numbers like that. So maybe the calculator is active. But there you go. So you need to show a step like that saying, hey, look, I did a right sum. It's right there. Okay, questions, concerns, comments, anybody? And by the way, I think I mentioned this earlier. I'll say it again. AP test, when it comes to like right sums and left sums and midpoint sums, I will say 100% of the time, you'll be given a table of data. The reason for that is smart young people that are good at programming their calculators to do things in the past have learned how to program their calculators to do left sums and right sums and midpoint sums, which is great. Like if you could do that, you definitely know what you're doing. But then what would they do with those programs? Sell them, give them away. People that have no idea what they're doing all of a sudden look like they do know what they're doing because they have this little program. And so, of course, the College Board is like, we have a problem with that. And I do too. You should know what you're doing if you actually look like you know what you're doing. So they'll give you these unpredictable tables of data. So anyway, we good? All right, let's keep on this theme of area and flip over. I think I know what's coming next. Yes. So I think you guys are really well conditioned to this. You guys remember... You guys remember at the start of the year when, we started doing like continuity and limits and all that? Remember how I insisted on like your symbology, and for that matter, my symbology and notation be precise? And I was like, you know what? If the limit needs to be there, the limit needs to be there. Like, remember how that was like such a struggle? Remember that definition of continuity? Limit from the left equals limit from the right equals value of the function. I got all kinds of stuff, like it would be, I would see this, limit x arrow to, and then this, and that would be equals f of x, and I would say, wow, there's a good attempt, but there's a lot wrong with that, right? What's so wrong with that?
It's missing what you're talking about.
Yeah, the limit of what, right? And, of course, the response is, well, I'm like, no, I don't. You need to tell me what that is. And so we put this in here, and now we start to feel a little bit better about this, but it's still not quite there. What's wrong with that? Something's wrong with it.
2.
It should be f of 2. That's right. So instead of f of x, it really has to be f of 2. It's not equal to f of x. And so do you see why the symbology matters? It so much matters. Let me remind you, math is a language, universal language nonetheless, right? Kids in China, you know, like when Sean Park came here from Korea, he didn't have to learn how we do math. Seriously. He just came right in, he maybe struggled with English, but it's, no, that comment.
I said, what?
What did you say?
I said, my friend free.
Oh, okay, I misheard you. Anyway, sorry, Tim, I thought you said something that you didn't. Anyways, like if we had, no, seriously, if we had a foreign exchange student just like join us from like Russia tomorrow, or tomorrow Saturday, but let's say Monday, they would be able to come right into our class. They would not understand anything English that I'm saying, but when I say, you know, when I like write x squared, they would know exactly what I'm talking about. They really would. So I say that to say our symbology needs to be correct, right? It's got to be so correct. And so this is a little bit symbology heavy, but there's a lot of the stuff you don't need to know how to do. So up there you can see there's the stuff about sigma notation, and we are going to be writing a lot of sigmas and things like that and matching things up with sigmas. So I'm hoping that from pre-calc you remember that sigma means basically one thing. Sum means to add stuff up. And so when you see sigma from 1 to n, just like this, and you got this little a sub I, that means you're going to be adding up n of these a sub i's. And it's vague on purpose, right? We don't know what it is, and we don't really care what it is. But notice it's a sub 1 plus a sub 2 plus a sub 3, all the way up to a sub n, and a sigma means we're going to be adding those things up. So sigma means sum or add. And then there's all these lovely little formulas down here, none of which you need to memorize, and to be frank with you, like none of which we'll use directly. I put these in here simply to say, you know, if you want to take some of these all the way through to their logical end, you'd need to know some of these formulas. I don't know that we're going to have the time for us to like do all that together here in class. I'm not going to expect you to do it on your own either. But if we do somehow end up with an extra 15 or 20 minutes, maybe I'll take you all the way through one of these and show you where these formulas would come into play. But for now, I want to kind of dig deep into this. This is going to be very conceptual. Okay, so if you're like thinking to yourself, my strength is adding and subtracting really well, that's not really going to come into play here. This can be very visual, very conceptual, okay? So put on your conceptual hats. You with me? Okay. So we're going to be finding area using the limit process, and I want to connect this back to your video. What we're going to do here is we're going to start transitioning a little bit, because the whole video and what we've done for the last few minutes has been about approximation, right? We're using these rectangles, and it's supposed to be like, sort of kind of close to the area. And I want to transition to an effort of, you know what, guys? Let's find exactly what the area is. Not pretty close or just, decent. Let's get the real area. Pretty easy for rectangles and squares and triangles. Not so easy with curves, right? So here we go. The video, I made this big deal. I can't remember exactly how many times I said it, but remember in the video I say something like, you find all the rectangular areas and then you add them. And then the next one is like you find all the rectangular areas and then you add them. You sigma, right? You sum them, okay? So here's what I'd like to do is take a look at this super intimidating looking equation right here. It says area equals. Now, I don't know if I can make a big enough deal about this, but this symbol right here, guys, if math were a religion, that'd be like the most holy figure in the religion, I think. It'd be one of them. Equals. Think about what that means, guys. That means the thing on the left side and the thing on the right side, even though they look radically different. I mean, honestly, can you imagine if we showed that to like a first grader? Said, hey guys, that equals that. I mean, wouldn't their objection be like, they don't look anything alike? It just says area on the left, and then there's these other symbols that are really confusing on the right. How could they be equal? Think about it. What that means is they have the same value, regardless of how they look. So let's think this over. Let's try to decide why these really are equivalent to each other. Let's look very carefully inside the sigma. I'll highlight this first piece in orange. Delta x. When you think about what was in that video and what we did a few minutes ago, a couple times with that table, we did some delta x's, didn't we? And if you want to peek back, that's totally fine. You can even look at that little picture on the right there. For all the stuff we did in the video, all the stuff we did just a few minutes ago, What did the delta x always stand for? Change in x, yep, but as far as rectangles go? No. It stood for the base, right? When we go back, flip back to that previous page, when we found the area based on this table to get our base length, didn't we say delta x was 1? Delta x was 2? Delta x was 4? Didn't delta x always stand for the base?
Yeah.
Okay, so that means this would be the base length of a rectangle. And then again, whether you're thinking about the video and all the graphs in the video, or you're thinking about the table, where did we get the height from? It was y values. Do you see anything resembling a y value? F of c, right? Isn't f of c an output? And so what I'm highlighting up here in a lovely purple color, that is your height. So guys, this looks scary. I get it. I really, honestly, truly get it. But if you really boil it down to what it is, it's sigma of rectangular areas. So in other words, let's add up all these little rectangular areas, and that'll give us an area. But there's a big leap to be had here. How on earth could this give us the exact area? Because we fully acknowledged before, this is just an approximation, right? How could I take my approximation and make it better with less error?
If it was instantaneously close to the thing.
Okay, but how many, so let's say, think back to all those examples we did, and even this one.
Infinite rectangles.
Okay, we're getting there. Even think about this, if we did rectangles like this, and I don't know, something like that. Obviously, I'm off as far as my approximation goes. What could I do with the number of rectangles to get it to be a better area? Skinnier rectangles, therefore more of them. So I've got 1, 2, 3, 4, 5 of them up there. What if I increase the number of rectangles on that little diagram to 20? They'd be skinnier, right? And wouldn't you think my error would be a little bit less? Well, if 20 is better, wouldn't 1,000 be better than 20? How about 1 billion? How about 1 trillion? What if the number of rectangles was approaching infinity? They'd be squeezed down to just be a single point wide, and now we're talking about actual true area. Not an approximation for it, but the actual area. And that's what this is all about right here. The limit as the number of rectangles heads towards infinity, that's what turns it into actual area. So, I'll get your question in a second. Believe it or not, all of those area formulas that you learned in geometry, like pi r squared, they're not fake. Do you know where they came from? Calculus. The area of a circle, the area of an ellipse, the volume of a cylinder, the surface area of a cone, blah, blah, blah. All those volume and area and surface area formulas that you were taught, it's not that Euclid just sat down and thought real hard about it and he's like, I'm going with pi r squared. Surely you know that's not the case. It was actually calculus that allowed us to understand that. Anyways, question from somebody. Kayla.
If your rectangles can get infinitely and infinitely smaller.
Skinnier. Let's say skinnier, because smaller makes it sound like they're short.
Skinnier, then can you ever actually have a precise correct area?
So that's what a limit is. Remember, a limit is not when the number of rectangles is infinity, the area is, because you can never have an infinite number of rectangles. We're just increasing the number without bound. So remember, a limit is talking about a pattern of behavior. So it's saying, hey, as the number of rectangles just gets bigger and bigger and bigger and bigger, where's the area headed to? And so we're talking about a limit, which does introduce the idea of as you get closer and closer and closer and closer to infinity, then the area appears to be heading in this direction. Yeah. Question?
Similar standpoint, if we had an equation like y equals 3, and we use this equation and found it from when x is 0 to x is 3, we would find exactly 9 as the area. It wouldn't be at 9.0000001. 9.
Yep. Like I said, if I have time, I'll show you. I'll show you a very familiar geometric figure, and I'll do it with a really familiar formula, and then we'll do it this way, and you'll see it's the same. Yeah. Pretty cool. Okay, so let's see where we're at. Okay, I think. We'll probably, if we have time, we'll probably do what you're asking about on like maybe day 1 of next week, something like that. Let's do this one right here. Like, you guys need a lot of touch points with this, so I want to run through this with you. So take a look at number 5. This introduces the term, and I think maybe I used this in the video, maybe Riemann sum. It's named after this guy, Riemann, who is credited with developing some of this, amongst other things. And so Riemann sums could stand for left sums, right sums, midpoint sums, later on trapezoid sums. We're going to write this official Riemann sum expression, not for an approximation, but for the exact area under the curve from 2 to 5. Guys, I want to just sketch out a graph super quick here for you. This is a standard cubic, like the parent graph for cubics. And so it looks something like this. And we're supposed to calculate, not approximate, the area from 2 to 5. So we're going to set this up. So I'm going to say that this is 2. And this is 5. So I want to give you kind of a system for doing this. Guys, I want to give you a very cut and dried system. And I think you do this more and more, you'll start to understand more and more about it. I want to give you a very clear system, and the system is this. We're going to start with the easiest possible stuff, work our way towards the medium difficulty stuff, and we'll finish with the most difficult. Okay? Make sense? Yeah. So if you are asked to write a Riemann sum, one of these Riemann sums for area under a curve, guys, here's the easiest part. Every single time, it'll involve this. Limit, as n heads towards infinity, of sigma from I equals 1 to n. That will be a feature on every single one of these, because if you think about it, what we're doing is we're summing up a bunch of rectangular areas, and then we're increasing the number of rectangles towards infinity. Every single one of them will have that. To me, that's the easiest part, because it's always going to be there. If you see write a, bless you, Riemann sum, bless you, and that's not a part of it, you got an issue. Like, every single one of them will involve rectangular areas being summed up, and the number of rectangles will be approaching infinity. They'll all have this. Okay. Now, that's the easiest part. I think the next easiest part, the medium difficulty, is the base length of every rectangle. So I want to just do a little illustration here real quick to help you understand. Let's say I've got this area, and I'm going to just sketch in 3 rectangles. So let me ask you this. If I did use 3 rectangles like that, what would be the base length of each of those rectangles? How'd you get that?
5 minus 2.
Yeah, 5 minus 2 is 3, so the full interval width is 3, right? So I'll just put that down here. Full interval width is 3. And there were 3 of them, so if we divvy it up evenly, they'd all be 1, right? So let's say we kept the same interval. Instead of like 3 rectangles, let's say I tried to sketch in 6 of them. What would be the base length on those 6? Maybe 3 divided by 6, 1/2, right? 0.5. What if I tried to somehow squeeze in 30 rectangles? The base length would be 1/10. So aren't you basically taking the full interval width divided by the number of rectangles to get the base length? So here's what I'm going to propose. My base for my rectangles is going to be 3 divided by the number of rectangles. Now I'm going to be flexible, and I'm going to say the number of rectangles is n. It's not going to be 3 or 6 or 30. It's going to be whatever I want it to be, because eventually I want the n to head towards infinity. So to me, the easiest part is limit sigma. The medium difficulty part is base length, because base length is simply interval width divided by n. It'll always be that. I mean, the 3 will be whatever it's going to be, but it's always going to be some number divided by n. And the hardest part is, what's the only thing left? The height. Okay, so would you guys agree with me? All this work that we put into this, I think, is going to pay off. Would you guys agree with me that the height of each one of these rectangles depends on one thing only? Doesn't it depend on the y value of the function? Like, doesn't the y value of the function say, all right, rectangle, you be this tall, you be this tall, you be that tall, right? And so the height is exactly tied to the y value of the function. So, what's the y value of this function?
X cubed.
And I'm going to say input cubed. Is that fair? It's going to be input cubed, and I'm getting that from right over here, of course, right? Y equals, the output equals, the height equals the input cubed. Make sense? So I'm going to just come over here and I'm going to say, all right, I'm not totally sure what my height is yet, but I'm going to say that it's going to be some input cubed. Remember, all this is limit sigma of base times height. Okay, so remember, the thing in here, I'll erase this in a second, this is just input cubed. So on my interval, my inputs can't be anything, right? Like if I told you that one of my inputs was like -4, that's impossible, right? Because -4 is not even in my interval. So let me ask you this. What is the lowest possible input that I could have on my interval? 2. I agree. So that's going to be the first number as part of your input. But then I'm not going to just stop at 2. Aren't I going to go from 2 to like a little bit more than 2? And then a little bit more than that, and a little bit more than that, a little bit more than that. I'm going to like work my way from left to right across my area. So every time I jump from 2 to the next one, to the next one, to the next one, to the next one, how far am I moving each time?
Infinitely small amount.
Okay, come on, keep. What am I like when I jump? I'm jumping to the next. So what would be the distance that I'm jumping? Not n, because n's the number of rectangles. 3 over n, isn't that the width that I have to jump to get to the next rectangle? I'd have to jump the width of a rectangle to get to the next rectangle, right? So I'm going to say, all right, 2 plus, and then I'm going to jump 3 over n. There's one last symbol we got to put in here, because if that's all I put, doesn't that cover like basically just the rectangle just to the right of the 2? What I need to do is put this. I need to finally bring this I into play. Because isn't the I going to go from 1 to 2 to 3 to 4 to 5 per the sigma? And so that I is going to allow me to start at the first rectangle, and then the second, and then the third. Literally, it's 3 over n times I. And here's why that works. If this right here is 2, then the next one would be 2 plus 3 over n as far as the input, right? Wouldn't the next one be 2 plus 2 times 3 over n? Because I jumped a second rectangle, then the next one would be over here would be 2 plus 3 times 3 over n, so on and so forth. Do you see how this is going from 1 to 2 to 3, and then it would go to 4 to 5 to 6? What's doing that, of course, is your sigma index, going from I equals 1 to 2 to 3 to 4 to 5, all the way up towards n. So guys, at this point, we've got it, right? So I want to just review this with you really quick. I tried to do this from easiest to hardest. Does that make sense? Easy. The limit sigma, always there. Medium, base length is always interval width divided by n. Height is the hard part. It's low input plus all your little steps to get to the end. Can you imagine that we might do this again on Tuesday? Or not Tuesday, because Tuesday's your quiz. Or wait a minute, when do we have class on Monday? You guys are Tuesday. So Tuesday's your quiz, right? So we'll do this again on Wednesday and probably Thursday of next week too. So anyways, hope you guys have a wonderful weekend. Meg. So if you don't have the I in there, then 2 plus 3 over n is simply 2 plus 3 over n. Thanks, Tim. So what the sigma does, the sigma naturally has the, thank you, Jake, has the I go from 1 to 2 to 3 to 4 to 5. So as I move my way, like I want to move my way all the way across this picture, right?
Yeah.
And if I just say my input, like literally what that is the x value for the input for this function to find your height. Okay. So if I just say, hey, my input is 2 plus 3 over n, I'm going to just simply be stuck on like the second rectangle.
Yeah.
Right?
Right.
And so I have to think to myself, like, what is a mechanism? Like, what is a method for getting me to go from this rectangle to this one, to this one, to this one, to this one, to go from the first to the second to the third to the fourth to the fifth? Well, isn't this I doing that? The I is going from 1 to n. And so if I multiply 3 over n times I, well, on the first go around, I will be 1, right?
Okay.
So that'd give me my first rectangle.
Yeah.
And then on the next term, because remember a sigma is a sum, so when I go plus the next one, well, now I is 2.
Okay.
And so I'd be multiplying by 2. That will get me from here to here. Now I'm on the second rectangle. And then after that, then I would go from 2 to 3. Now I'm to the third rectangle, so my input would not just be a 2. It wouldn't be a 2 plus 3 over n. It would be 2 plus 3 over n plus 3 over n plus 3 over n, that would give me my input. Remember, the height is based on the input.
Okay. So how does I like stop at 5 though when you're doing this equation?
Great
So-
question. So I doesn't stop at 5. It doesn't need to stop at 5 because n is actually heading towards infinity, right? And so if n is heading towards infinity,
Thank you, Mr. Anderson.
thank you, Kayvon, the number of rectangles is actually getting skinnier and skinnier and skinnier and skinnier,
Okay.
like a width approaching 0, right?
Yeah.
And so, yeah, like the I being, like I is, so like I think what you're thinking is that the I is the x value.
Okay.
It's not. 2 plus 3 over n I is the x value. So 2 is the x value, right? It's like right here. 2 is the x value. And to get from one rectangle to the next, like, do you understand how I've got to add 3 over n to get to the next rectangle?
Yeah.
So the question is, like, how many of those do I need?
Right.
Doesn't it depend on how wide the rectangles are?
Yeah.
So if I told you the rectangles were 1 wide, I would only need 3 of those,
Okay.
right? If I told you that the rectangles were like 1/10 wide, I'd need 30 of those. But what if I
Yeah.
told you that the rectangles, and listen, what if I told you the rectangles were approaching a width of 0?
Isn't that what this is saying?
Yeah. And
Okay.
so your question was like, how does it know to stop at 5?
Mhm.
Well, as the number of rectangles goes towards infinity, causing the width to be heading towards 0,
Yeah.
then I need an infinite number of them. So in other words,
Okay.
n has to head towards infinity, so I will go from 1 towards infinity. I'd need an infinite number of them.
But then, what would be the difference? Sorry, what would be the difference between finding it like when the interval stops at 5 and the interval stops at 10? Like, how would that be different in this equation?
Oh, it's this right here.
The 3.
Yeah,
Okay.
it's your interval width.
Oh.
And this, like both of these 3s.
Okay. Okay.
Yeah, good question, good question. Otherwise, you're right. Like, why wouldn't it just keep going towards a million?
Yeah.
Right, so we're saying here our interval width is 3. Our interval width is 3, and so regardless, so regardless of what I is doing, you're never going to go past 2 plus 3, right?
Yeah.
Because like as I heads towards n, the n's would cancel, right?
Mm-hmm.
You'd get 2 plus 3 is 5.
Okay.
If this was a 7, then as the n's would like head towards canceling, you'd get 2 plus 7, which would be 9.
Okay. That makes sense.
Make sense? Okay,
Yeah.
cool. Yeah, good question. It usually takes a little while to like really